If you've been unlucky enough to have planned a PC build in the past year, you'll have undoubtedly noticed the egregious spike in RAM and storage costs. These days, people are settling for DDR3 RAM, a speed standard that's at least 2 generations behind, and even that is becoming hard to come by. I personally wanted to build an editing server this year, and that requires not just fast SSD storage, but also current generation RAM for caching. In times like these, one might naturally start to wonder, how important is computer memory really? Is there a way that we can replace it, or even go without it? Let's get the boring stuff out of the way first. You've probably already heard about swap or page files. The terminology varies by operating system, but the concept is more or less the same. When your computer starts running out of free memory, it will kick in a contingency plan that swaps some of the lesser used memory pages to a file or block device. This effectively moves some of your RAM into the disk. And to be clear, whenever I say disk, I'm talking about any kind of non-volatile storage, including SSDs, SD cards, and even flash drives, not necessarily just actual spinning disks. Now, this concept is nothing new. It's been around since the 1960s, which is why I'm grouping it in with the boring stuff. You've more than likely heard of it already, and it's not really what this video is about. It doesn't actually let you replace memory either. The processor can't read directly from the disk, so it needs RAM to swap the disk contents in and out of memory. We'll get to exactly why that's the case a bit later, and also how to work around that, but for now, just pretend that this is fact. So, if we can't get rid of all RAM this way, we can at least decrease the available memory to a near zero amount. This way, there's still some RAM for the CPU to function, but the vast majority of actual data sits on the disk. To try this out in practice, we first need to limit the amount of memory available to the operating system by a ridiculous amount. On Linux, this can be done with just one boot parameter. I started at a value of 256 megabytes, which I figured was a rather conservative amount. But actually, when I tried rebooting the system, it froze while allocating the initial RAM disk. This to me was somewhat unexpected. Smaller devices like this here Lychee RV Nano only have a total of 256 megabytes on board, and half of that is reserved for camera and display drivers, yet this thing boots into a functional Linux shell in just a few seconds. Though, to be fair, my desktop PC probably has quite a bit more stuff to load. Because my computer was now unbootable, I had to remove the SSD and connect it externally to my laptop, from where I could then manually fix the boot configuration. Next, I tried bumping it up to 384 megabytes, which still didn't work, and after that, I finally settled on half a gigabyte as the magic number. Now, yes, this isn't even close to zero RAM, but for the sake of this demonstration, it'll work just fine to choke the system. Then, to finish the setup, I disabled one of my swap partitions, leaving me with practically no RAM and just 4 gigabytes of swap on my SATA SSD. Now, you might be wondering why I didn't try the more competitive NVMe SSDs, and the simple answer is that I don't have one, and I'm not going to be buying one anytime soon. Anyway, what exactly is this demonstration that I'm setting up for? Well, the plan is to run 3 different stress tests to show just how much of a difference you can make by replacing RAM. The first test is a browser benchmark called Speedometer. This basically simulates normal, everyday website usage and measures performance across different metrics. So that'll be our stand-in for normal computer use. The second test is just a plain old memory access benchmark. This will hopefully give us some raw numbers to compare irrespective of surrounding context. And finally, the third test is a Portal 2 benchmark to act as a stand-in for casual gaming. I'll remind you, this game came out in 2011, so even a modest computer shouldn't struggle too much with this. As for environment, the browser benchmark targets plain unmodified Chromium on an incognito tab to prevent caching. The memory benchmark tests 2 GB blocks across a max total run size of 512 GB, and the Portal 2 benchmark is run on Vulkan using the highest graphics settings. For a control, I ran each of these tests with 4 GB of actual system RAM and a tiny bit of swap just to prevent the OS from locking up. And, as already discussed, I then ran these same tests with almost no usable system RAM and 4 GB of simulated RAM on the disk. Okay, so let's break down these results. Web browsing on this setup isn't impossible, you just need a lot of patience. If you've ever used a cheap Android phone from like a decade ago, you'll know what I'm talking about. The raw memory test doesn't really tell us that much. I mean, obviously a SATA SSD is going to be slower than DDR4 RAM. Though I will point out that this test only managed to finish one transfer operation, as opposed to the 55 from the control. Finally, the Portal 2 test. Even just trying to navigate Steam was a nightmare, which likely isn't too surprising once you consider that Steam's UI is basically just Chromium in a disguise. But once I did get to the game's library page, clicking the start button would just crash Steam. There was no pop-up or anything. It didn't even really start launching Portal 2. Unlike the other tests, this result isn't caused by the speed of the memory. Instead, it's a fundamental limitation in how swap works. The way I think about swap is like a juggler. At any one point, the juggler only has one ball in their hands. This represents the system's physical memory, while the rest of the balls are in the air, away from the juggler. This represents the swap space. Now, this is fine for simple web browsing, but what if a game's texture or model requires 2 balls worth of memory? A juggler can access 1/2 of the asset at a time, but in order to operate on the whole object, the juggler has to be able to handle the whole pair of balls at once. This is actually the same problem that I ran into in my video about running Portal 2 on a controller. The only way I could get the game to run was by manually simplifying the map files and assets. Either way, with this level of performance, even if Portal 2 did launch, I wouldn't consider this system usable. Perhaps it would have been better with an NVMe SSD, but again, I don't have one. What I do have, however, are a few spare graphics cards lying around. Some of these were used by the dinosaurs, and others I picked up on AliExpress for the price of an airport coffee. But today, we're not interested in the graphics strips themselves. We're interested in the video memory, or VRAM. Unless you're running some kind of mobile setup, chances are your GPU has its own dedicated cluster of memory. I think you see where I'm going with this. It is possible to access this memory as raw bytes thanks to the OpenCL API, which means that we can technically read and write arbitrary data. The only problem is that this is once again happening at the operating system level, which means that we once again cannot outright replace RAM with VRAM. However, thanks to this GitHub project by Alexander Overvoord, we can set up a fuse file system on the GPU, which can then be used to host a swap file. In other words, this program called VRAMFS creates a bunch of functions for reading, writing, and listing files. The operating system sees these as a perfectly normal way to interface with a new file system, but in the background, these functions are being translated to the GPU's video memory. So we can effectively repeat the same experiment as before, using disk as RAM, but instead of actually writing to the disk, we're writing to the graphics card. Now, setting up this experiment didn't go as smoothly as the last one. I once again limited my system to just 512 megabytes of system RAM, same as before. But when I tried to mount the virtual file system, my entire desktop crashed. At first I thought this was because I was tampering with video memory that was being actively used by the desktop environment. After all, the GPU in my computer has only 6 gigabytes of VRAM. Since I'd been using 4 gigabytes in all of the other tests so far, it would only be fair to allocate 4 gigabytes here too. But that leaves me with less than half of my VRAM to use for actually rendering stuff. Still, this explanation didn't make too much sense, because a single monitor 1080p desktop shouldn't be taking up 2 gigabytes of VRAM anyway. I tried running the program again, but this time in a pure virtual console, outside of a graphical interface. And this time, I got far more meaningful output. It turns out the file system emulation itself has to allocate a bunch of memory, which, using the analogy from before, spans several of the juggler's balls. The system panics, and to save itself from starving, it decides to randomly kill a whole bunch of processes until it's in the green again. And it just so happens that it first kills my GUI, and only when that doesn't work, it finally tries killing VRAMFS. There's really no clean solution to this but to up the system memory once again. This time I set it to 1 gigabyte, which might not sound like very little, but keep in mind that most of this is now going to be occupied by VRAMFS and the operating system itself. So our test suite is still going to be largely forced into using swap. Trying it now, I can indeed successfully mount the VRAM file system. It's worth noting that I can't actually just put the swap file directly on Fuse. Instead, I create a loopback device that adds another layer of software emulation to the chain, but after that's said and done, I do finally have a swap file on VRAM. Now I carefully disconnect all of the actual disk swap, so only the GPU share is left along with whatever little bits of system RAM remain. Okay, so what about the tests? Depending on how you were thinking about this configuration, you might be surprised to see these results. On one hand, my GTX 1660 Super uses GDDR6 memory, with a theoretical bandwidth of 336 GB per second, which obviously outpaces even the best SSDs. But on the other hand, there's just so much more CPU overhead in this whole setup. Think about it. When using actual swap, the operating system is using very common routines for directly reading and writing to a hardware device. But in this setup, the operating system first has to resolve the loopback block device, which points it to a Fuse file system, which then redirects it to a function on a user space program. This function then asks the OpenCL API to fetch a specific portion of video memory, and only then does this chain finally reach the GPU. This whole process happens over and over for nearly every memory request, and that's on top of having to swap in and out of system RAM, so it's no wonder that the browser test took over an hour to finish. The memory benchmark just froze the computer, and I didn't even bother with Portal 2. As you can imagine, going any further with this likely isn't a great idea, but I do want to note a few honorable mentions. You might have heard the meme of downloading more RAM, and the various consequent implementations of that, including mounting a Google Drive volume as swap space. Now, I don't think I need to point out why this is a terrible idea, but just to be thorough, not only does networking introduce a monstrous amount of latency, you also need memory to use the network. It's a silly idea, but also one that's frankly not even worth testing. You might also be asking why I didn't use a virtual machine to run my tests. In theory, if the reason we can't replace RAM entirely is because of a hardware limitation, then maybe custom virtual hardware could be the answer. But in reality, no mainstream emulator will let you route all RAM to the disk. It just doesn't make any sense. And even if you could, the host machine and the emulator itself still use RAM for executing instructions and caching data, so it's not really a fair comparison. Some of you might have also been yelling at your screens waiting for me to bring up Intel Optane. In short, Optane is a now discontinued implementation of non-volatile random access memory, or basically a hybrid between RAM and SSD, though yes, I know that's not an entirely accurate analogy. Reportedly, some versions could even connect directly to a standard DIMM slot, which is likely the closest we'll ever get to plugging an SSD into a RAM socket. Though, if our goal is to save money by replacing RAM, Optane likely isn't the right solution, at least not anymore. But the cost of RAM and storage is not the only risk posed by our rapid advances in artificial intelligence. As these models get smarter, they also get better at hacking. In times like these, humanity really needs cybersecurity. If only there was a hands-on way to learn and practice cybersecurity with... Hold on, that's the sponsor of today's video! TryHackMe is a cybersecurity learning platform where you get to skip the theory and jump right into the shoes of a white hat hacker. It is the place to practice ethically hacking real systems, as in you can literally break into a virtual machine simulating real scenarios that actually happened, so you can then develop skills for defending against those kinds of attacks. And those are the kinds of skills that are being actively sought out by high-paying employers in the tech industry, because the reality is there are far too few cybersecurity experts in the field right now. And the best part is that you don't have to have any prior knowledge to get started. TryHackMe has a streamlined roadmap that takes you from complete beginner to professionally certified. And unlike what's seen in many movies, you don't need a supercomputer to do any of this. TryHackMe works from just a regular browser on even the simplest of laptops. It could probably even work without RAM. Okay, well, maybe not that last one. If any of this sounds at all interesting, you can actually start right now, completely for free. They've got lots of starter challenges for you to try out in case you don't want to fully commit right away. Though, of course, the real meat is in Premium, which gives you full access to the entire platform. If you're serious about cybersecurity, then in the long run, it basically pays for itself. TryHackMe isn't just for learning core concepts. It can get you real professional certifications that are recognized in the industry. To sweeten the deal, they're giving y'all a 30% discount. That's like a third of the price off. All you have to do is click the link in the description and use code RUNNER30 when signing up for Premium. Okay, it is finally time to talk about the real premise of this video. How do you run a computer with zero RAM whatsoever? To answer that question, we first have to take a look at why RAM exists in the first place. One of the simplest models of what we call a computer is the Turing machine. The concept is straightforward. You're given an infinitely long reel of tape, which starts off containing some input. This tape is then given to a simple machine, which updates its state based on the symbols that it sees on the tape. Sometimes a state change may trigger it to read a different part of the tape, or to overwrite a part of the tape. In the end, after the machine reaches a terminal state, the tape will contain the machine's output. In modern computer terms, the machine is a CPU, and the tape is kind of like a hard drive. This model is famously capable of handling any computable task, provided you have that infinitely long tape reel. But notice how there's no mention of RAM anywhere. While the tape is a form of memory, it's not random access memory, which is what gives RAM its name. The key difference is that a reel of tape, or a hard drive, or really any mechanical storage medium has to physically walk to the destination address, whereas random access memory can instantly jump to any address at random. So yeah, modern day RAM really only exists because other types of memory are too slow. From what we saw before, this checks out. Even partially replacing your RAM with an SSD slows things down tremendously. But believe it or not, RAM on its own is still considered slow, and this is partially to do with the speed of light. See, on a computer motherboard, your CPU is here, while your RAM is all the way over there. While it might not seem like much, this distance is a relatively big source of latency, simply because electrons can only travel so fast through the copper traces. That's actually why RAM is always positioned so close to the processor. It would cost latency to place it any further. To counter this bottleneck, the engineers of computer processors decided to put their own high-speed memory inside of the CPU, which acts as a cache. So whenever your processor reads instructions from RAM, it doesn't do so one by one. Instead, it loads a whole bunch of instructions into this cache and then works off of that. Now, if we could just figure out how to make the CPU use just the cache, we could technically run a computer without a single RAM stick installed. Granted, CPU cache is rather tiny. My Ryzen 5 3600 has 3 layers of cache, with at most 36 megabytes total, and that's assuming you use it right. But for a simple proof of concept, even just one core of L1 cache is plenty. Really, the main issue is in getting the CPU to cooperate. Computer processors are really dumb. On their own, they do absolutely nothing, because they have no instructions to follow. Even if you gave one a hard drive with a bunch of programs, it wouldn't know how to read that hard drive. If you gave it RAM, it wouldn't know how to use that RAM. A CPU needs to be explicitly babied into doing literally anything, and that's the job of the BIOS. Every motherboard has a little chip on it containing a very small program, which tells the processor how to initialize RAM, how to initialize PCI devices, how to access the hard drive, and finally, how to boot a real operating system. The BIOS is the very first set of instructions that a processor encounters. So technically, if we take control of the BIOS, we can tell the CPU to ignore all other peripherals and instead initialize its own cache, and run a small program inside of that cache. To do this, I'll be cloning the open source BIOS project coreboot to act as a jumping off point. This actually simplifies things a lot, because one of the earliest stages of coreboot's initialization involves setting up cache as RAM. This means that all we really have to do is interrupt it before it leaves that stage, and run our payload instead. Even so, I really thought I'd have to write some funky assembly to get this to work, but it turns out it's really as simple as just adding a couple lines of C. Right away, the very first thing I did is write a brainfuck interpreter, just to see if I could run some actual calculations and do a bit more than print text on screen. And once that worked, the logical next step was to port an NES emulator. If you squint hard enough, you can almost recognize Super Mario Bros. Being rendered in ASCII art. Now, ideally, this would output to some kind of display, but remember, this code is being executed long before any video interfaces would be initialized. The only I/O peripheral that we have access to is the common serial bus. On older motherboards, that's the connector that looks kind of like VGA, but with 2 rows of pins instead of 3. It's an incredibly simple interface, only really capable of sending and receiving text. But by using some special characters, it's possible to instruct the receiving terminal to render those characters in different colors. That way, we can basically have a low-resolution screen be sent over this simple serial bus. Now, so far, I've just been testing this stuff in an emulator, but once we get to real hardware, the restrictions become a lot more narrow. The Super Mario Bros. ROM is 40 kilobytes, which far exceeds the L1 cache of older hardware. I could try to optimize it or read directly from BIOS flash, but instead, I wrote a small snake game to work as a simpler proof of concept. Speaking of hardware, how do we get a real BIOS chip to run our custom code? Nowadays, most motherboards have write protections on the chips, and often strictly prohibit the operating system from even touching the BIOS flash. On top of that, modern machines don't even have a BIOS. Instead, they use UEFI, which is a bit more convoluted. The short answer is just don't use a modern machine. This here is the motherboard of a Dell Latitude D630 laptop, which came out in 2007. Its BIOS chip is completely unlocked and it has a built-in serial port, so it would seem like the perfect candidate for an experiment like this. The only problem is that coreboot doesn't explicitly support the D630, but, you know, I figured that if I selected the second closest option, it might work just enough to get us to our payload. Keep in mind, I don't need all of coreboot to work. I really only need the first couple of stages. Also, because the chip is soldered on the board with tiny contacts, I would need to buy specialized hardware to flash it externally. Luckily, this board has no protection whatsoever, which means that I can flash the chip from within Linux. Though, doing this also means that I've only got one shot. If I mess this up, I won't be able to boot into Linux again. This here is a remote shell into that computer, and I'm about to run the flashing tool. Hitting enter on this command was way more stressful than I could have anticipated. If the ROM turns out to not work, I've essentially bricked the motherboard with zero benefit. All that was left was to open up the serial monitor and hope that something shows up. Nope. No signs of life. Yeah, so I ended up ordering that BIOS flasher anyway, but in the meanwhile, I went digging around my junk for another motherboard that might be more compatible. And somehow, I struck gold. Okay, so our victim today is this ASRock board from 2009, I think it was. It's a G31M-GS, if you want to go look it up yourself, but to sort of give you an estimate of how old this thing is, it's got dual-channel DDR2 memory at 800 MHz. And I've actually got the sticks right over here. These are each 512 megabytes, so total this thing would have shipped with 1 gigabyte, which, I don't know, probably ran XP or Vista or something, but today we don't really care about the RAM for obvious reasons. It's also got 2 PCIe slots, a by 1 and a by 16, and also 2 PCI slots, so not PCIe. But I guess more importantly for us, this is the only board that I own that is actually compatible with coreboot. Well, kind of. Technically, it's the G41M that's compatible fully, but I think the only difference is really the flash size because it works just fine on this one too. And also, it's old enough to have a serial port, which will be important for reasons that I mentioned before. And this one, purely out of chance, I didn't buy this motherboard for this video. It just so happens to have a detachable BIOS chip. So if I go in with a screwdriver carefully here, I can actually take off the very chip that holds the BIOS program. And this also means that in order to flash it, I didn't have to buy specialized hardware. I could just use a breadboard with a microcontroller and a few wires, and then just sort of slot it in the middle here. And then if I have a custom program on the microcontroller, I can use that to then flash this chip. So I mentioned that I had to buy a special tool for the latitude so that I could unbrick that motherboard, but while I was waiting for that to arrive, I could just, flash this thing from just a regular microcontroller that I had lying around. Okay, so I've connected the board up to an old power supply I had lying around, and for this, we really don't need much. We just need a 20-pin connector for the motherboard power and a 4-pin connector for the CPU power. We don't even need the RAM sticks for obvious reasons, and we don't need any other peripherals except for the serial port, and that's going to be connected through these cables here. So one end goes into the motherboard, and then the other end is going to be going into a USB to serial adapter, because I plan to connect this up to my laptop, and my laptop does not have a serial port because it's a bit too new for that. Now, technically, this does mean that my laptop is going to be acting as a sort of display for this board, and while my laptop does have its own RAM, I want to make it clear that all of the computation for the Snake game is happening on this here motherboard, on this CPU with no RAM installed. Okay, so I'm going to flip the power supply on, and I'm going to short the power button pins with a screwdriver. And there you go. So the CPU fan spun up. You saw some debug messages there from core boot. And as you can see now on my laptop, I can control what is effectively just a very small Snake game clone. And again, this is all running on this board here, not on my laptop. You can see there's nothing else connected here. It's just this serial port going into this USB adapter straight into my laptop. And then this terminal window is just showing the characters that are being sent over that connection. And yeah, I mean, it's not running great. There's actually no delay added between like the Snake's movement. This is literally just how slow the game is running on that CPU. And I think that's because of the speed of the serial bus. I think there's just like a bunch of waiting to make sure that the buffer is flushed or whatever, but I'm not entirely sure about that. And I think if I hold a key, it like basically pauses the game because it's like trying to handle all the inputs that are coming in. Okay, now I'll take this opportunity to test something that I haven't actually tried before, which is what happens when you remove the BIOS flash while it's still running. Ooh, okay. So, yeah, there you go. I removed the BIOS strip while it's running and the game just froze. I actually kind of expected it to just keep going because I figured that the game is probably loaded into CPU cache. But no, it just stopped. Maybe there's some like CPU interrupt that gets fired whenever you remove the flash. I'm not entirely sure on that, but hey, it's the voiceover again. Turns out, this CPU doesn't support caching the ROM. It even says so when it's booting up. So that would explain why removing the chip freezes it, and also why the performance is so terrible. It's constantly reading instructions from flash. Of course, this is just a proof of concept, but you definitely could run more complicated stuff if you initialize the hard drive and treated that as memory. But this video is already long enough. Oh, and before you go, I want to let you know that you can now schedule a one-on-one call with me. Whether you want to learn programming with a private tutor, or consult about a project you're working on, or even just talk about something that I might be knowledgeable in, you can now pay me money to book my time at learn.p2r3.com. Thanks again to TryHackMe for sponsoring this video. If you're interested in cybersecurity, definitely do go check them out. Again, links in the description, code is runner30, you'll get 30% off an annual premium sub. Thanks for watching.